Welcome to our geometry lesson 4.6, Isosceles Triangles and Equilateral Triangles. Before the fact that triangles were isosceles or equilateral, now we're going to go ahead and use various properties that we'll learn today of both of those triangles. Let's look at the first theorem we're going to learn today on the isosceles triangle. 4.10 states the isosceles triangle: if two sides of a triangle are congruent, then the angles opposite of those sides are also congruent. So in other words, if we have side AC, which is congruent to side CB, that tells us the angles opposite to each of those sides. So in the case of BC, 1, in the case of AC, 2, those opposite angles are congruent as well. And remember, that's only the case for isosceles triangles. If we look at the converse, if we have two angles, 1 and 2, we can say the sides opposite of those angles are congruent, as long as 1 and 2 are congruent. So if 2 is congruent, then the side DE would be congruent to the side FE, which is opposite angle 1. So in this example, we have named two unmarked congruent angles. So we see that C and D are marked, so we're looking for two angles that aren't C and D to call congruent. Well, immediately I see these two sides marked as congruent, and based on the theorem we just went over, if I look at this side, or this angle opposite of side CB, and this angle opposite of side AB, we're going to look at angle BCA and also angle A. Notice we couldn't just call it angle C and A, because when we're talking about this C, are we referring to this angle or are we referring to this angle? That's why they went out of their way to name it BCA, to clarify that angle. Example, name two unmarked congruent segments. Again, I would, using our theorem, or our converse of that theorem, I would think to look for two marked angles, because we can't use because we know they're marked. So they not really sure why they would consider this unmarked, but I am using that theorem to call BD one of those unmarked sides, and we know that because C and D are congruent, segments BC and BD are opposite those angles, so they're congruent as well. So go ahead and pause the video to check your progress here. Which statement correctly names the two congruent angles? And hopefully you chose answer B. We want JMK and JKM to be congruent, because we see that sides JM and JK are congruent, and those are the two angles that are opposite those sides. Which statement correctly names two congruent segments? The correct answer is D, because this angle is congruent to this angle. The opposite side to angle PKL would be side PM. The opposite side to angle PML would be side PK. We have a proof for our isosceles triangle theorem. We are given that LMP is indeed a triangle. We're also given that LM and LP are congruent, so we know it's isosceles. We want to prove that angle M, so this angle here, is congruent to angle P, this angle here. So let's just call N a midpoint. It wasn't given to us, but we're just going to put that out there. We're going to call this midpoint N, and make this segment here LN. So those are our first two steps, because we know that 2 points make a line. we have point L and point N, we can make a line. Now, since N is our midpoint we defined, we know that M has to be congruent to Pn. We also know that En that has the side Ln, so this triangle as well as this, both those contain Ln, so we use the reflexive property to show that that line is equal or congruent to itself. Since we're given that this segment LM is congruent to LP in step 5 there, we can use side, side, side to LMN, so this top triangle is congruent to LPN, this bottom triangle. And because this last part, congruent parts of congruent triangles are equal, because we just showed that all sides are equal by midpoint theorem, the theorem we just learned about isosceles triangles, and reflexive property, we can show that this angle M does in fact correspond with this angle P. So looking at a couple corollaries here for equilateral triangles, corollary 4.3 states that it defines a triangle as equilateral if and only if it's equiangular. So there's no way to have non-equal angles on all 3 points if you don't have an equilateral triangle. So that kind of, we can extend that. A triangle must have its angles add up to 180 degrees, and all angles must be equal. We can make this corollary 4.4, saying if all the sides of this triangle are equal, then all the angles of the triangle must in fact equal 60 degrees. So let's go ahead and put this to work in an example for us. If we want to find the measure of angle R, we know that this angle Q is 60 degrees. That doesn't necessarily tell us that P and R are both 60 degrees. They could be like 50 and 40 as long as they add up to, or I'm sorry, more like 50 and 70, so they could all add up to 180. Just because it's drawn to look very equilateral doesn't mean it's necessarily to scale. But what we do know is both these sides are equal. PQ and QR are 5 centimeters each. So opposite angles have to be congruent. So the triangle sum theorem, since those two are equal, up to the remaining sum after this 60 degrees, R have to add up to 120. The only way those can be equal and add up to 120 is if R 60 degrees each. So angle R and angle P are 60 degrees. If you want to take a look at this in detail, you may go ahead and pause the video, but we're going to move on for the sake of time. So now finding PR, we in fact now know that we have 60, 60, 60. It's an equilateral triangle, or equiangular triangle. Therefore, it must also be equilateral based on the corollary we just discussed. So PR must also be 5 centimeters. So let's go ahead and pause your video here, check your progress, find the measure of angle T, and hopefully you chose 60 degrees because we have these equal sides, and that means if this one has to match angle T, which is 60 degrees. So finding TS. And hopefully you see that TS is indeed 3.5. Because if this is 60, this must be 60. We have an equiangular triangle. It must also be equilateral, so that side TS must be 3.5. Now let's look at a question involving algebra. Find the value of each variable. We have this triangle DEF, and its one side is 6y plus 3. It has a side 8y minus 5, and those are equal. So as soon as I say I'm going to set 6y plus 3 equal to, let's do our algebra here, add 5. So both sides 2, we get 4 equals y. So now the other thing we need to find is what 4x minus 8 is. And setting the two angles, setting 4x minus 8 equal to 4x minus 8 isn't really going to help us much. So we're going to need our reasoning ability here. We do know that those are equal angles. And angle F are equal. Well, we also know, based on our theorem, that if the sides are equal here, their opposite angles have to be equal. So this also is equal to that. We see we have an equilateral triangle. So that this angle also is 4x minus 8. So since we have 3 4x minus 8s that have to add to equal 180, this is the angle for x minus 8. Didn't have to do that because what's going to happen is when I divide by 3, it's an equilateral triangle, I can set one of those angles to 60. So let's add 8 to both. We can divide both sides by 4 to get that x equals 17. We found the value of 4 to be y, the value of x to be 17. Alright, so go ahead and answer the question, finding the value of each variable in the same way. I chose B because it is an equilateral triangle. It has to be 60. 3 times 20 is 60, so it has to either be A or B. Then when we see that these two sides are equal, 8 is equal to 2y minus 6. So 2y has to eventually equal 14, which is 7. Alright, so let's see if we can get this last proof in 3 minutes here. We're given that hexagon is a regular polygon, so all the sides are equal, all the angles are equal. Triangle ONG is equilateral. N is the midpoint of GE, and so in other words, N is the center, and EX is parallel to OG. We want to prove that triangle ENX is equilateral. So what we're going to do is a regular polygon, and that ONG is equilateral. Like I said, a regular hexagon, all those sides are equal or congruent, and we know that N is the midpoint of GE. N is the center. Because of the midpoint theorem, we can know that that line segment that's divided by the center, so NG and NE are both congruent, and we're also given that EX is parallel to OG. When we look at this, we know that because those two lines are here and OG are parallel, we know that this angle has to equal this angle. We know that this angle has to equal this angle. So because of that, we're going to use alternate exterior angles theorem to say NEX. And hopefully you have this diagram in your notes, but angle NEX is congruent to NGO. And by side angle side, we can then say triangle ONG is congruent to triangle ENX. So segment OG is congruent to NO, which is congruent to GN, because it's an equilateral triangle. We've just proved that all the sides are congruent. And because congruent parts of congruent triangles are congruent, we can then say that NO is congruent to NX and G congruent to EN. Since XE and NX and EN are congruent, we can substitute those all in for one another, and the definition of an equilateral triangle tells us that ENX is equilateral. So I know I do that fast, but I only have about 30 seconds left. Take a look at this proof here. Go back and pause if you need to, but after you've taken it, and this should also be in your notes, but go ahead and figure out which reason you can put in for number 5 there to complete this proof. And I apologize for rushing, but you can get these notes full on Edmodo. Thanks for watching and have a great day.